Kinetic of particles, energy methods. In this section, I'm going to talk about the work done by particular forces. When objects move from position 1 with coordinates x1, y1, z1 to position 2 with coordinate x2, y2, z2, the force exerted by the object's weight is negative mgj. If we consider only weight act on the object, the work done by an object is weight. And we have work equal negative mg times y2 minus y1. As you can see, the work is independent of the pass from position 1 to position 2. The work is negative if the height increase and the work is positive if the height decrease. By Hooke's law, we can find the force of a spring. The spring force equal spring constant times the formation of a spring, or F equal K times X. The work done on an object by a linear spring is negative 1/2 K times x2 squared minus x1 squared, where x1 and x2 are the value of the stretch of the spring at the initial and final positions. As you can see, the work of a spring is independent of the pass from x1 to x2. Work of the force exerted by a spring is positive when x1 bigger than the x2. Also, the work of the force exerted by the spring is equal negative of area under the curve of F plot against X. Let's look at some examples. Suppose that you stand at the edge of a 200 feet cliff and throw rocks at 30 feet per second in the three directions shown. Neglect aerodynamic drag. Use the principle of work and energy to determine the magnitude of the velocity of the rock just before it hits the ground in each case. If we neglect aerodynamic drag, the only force doing work from position 1 to position 2 is the rock's weight. So we can apply the principle of work and energy to determine its velocity before it hits the ground. As I mentioned at the beginning of this video, the work done by force, gravity, or weight is independent of the pass from 1 to 2. Therefore, the velocity for different angles are same and doesn't depend on the initial angle. So, by applying the principle of work and energy, we find the velocity of the rock before hit the ground. So the velocity is 170 feet per second. Next example. The 2 kilogram ball is released from rest in position 1 with the string horizontal. The length of the string is 1 meter. What is the magnitude of the ball's velocity when it is in position 2? Again, the work done by weight is independent of the path from 1 to 2. So the vertical distance between the position 2 and position 1 is negative L sine 40 degrees. L is the length of the string. Now we can find the work done by the ball from position 1 to position 2. The work is 12.61 Newton meter. So we can apply the principle of work and energy to determine its velocity when it is in position 2. The velocity in position 2 is 3.55 meter per second. Last example. The 400 kilogram hammer is lifted to position 1 and released from rest. It falls and strikes a workpiece when it is in position 2. The spring constant is 1,500 Newton per meter. And the springs are on stretch when the hammer is in position to neglect friction. What is the velocity of the hammer just before it strikes the workpiece? Okay, first we have to calculate the work done by the weight. The hammer falls downward, so the work is positive, and its magnitude is the product of the weight and the change in height. So the work of the weight is 157 Newton meter. Now we have to calculate the work done by each of the springs. The springs are on a stretch in position 2, so S2 equals 0. So the work of the spring is 30 Newton meter. Now we apply the work and principle of work and energy to obtain the velocity of hammer in position 2. We have the work of the weight and work of the spring. But we have two springs, so we have 2 times 2. So 2 times work of a spring equal the kinetic energy. Now we can find the velocity of the hammer at position 2. So the velocity is 3.29 meter per second. Thank you for watching.